Before we can move forward and talk about bonding, we need to talk about something called valence electrons. So we're still working with our electron configurations, and now we're actually going to use those configurations to figure out how many valence electrons an element has. So first, let's define a valence electron. A valence electron refers to the electrons in the outermost or the highest energy levels. Remember, our energy levels are 1 through 7. So if you have an element and you write its electron configuration and its electrons end in energy level 3, that would be its highest energy level or its outermost shell. If we think about Bohr's model of the atom, each energy level was a shell, a layer around our nucleus. So you'll hear valence electrons referred to as in the highest shell, in the outermost shell, in the highest energy level. It all means the same thing. The number of valence electrons also determines the number of electrons available to bond, or how easily an element is going to bond or react with something else. And that also refers to the combining power of an element. So we're going to look at how elements start to combine together, how they start to bond with each other. And all of that is influenced by how many valence electrons an element has. So let's look at some examples. So first of all, I want to refresh what an electron configuration looks like. So there are 3 parts to each chunk of an electron configuration. The big number that comes first, remember, that refers to our energy level. The letter, the S, P, D, or F, refers to the orbital, and so remember that that's the shape of the electron cloud. And then the small number up here is the number of electrons that are in that orbital. We're going to focus on the energy level and the number of electrons. We're not going to worry about the orbitals. We're just going to be focusing on finding the highest energy level and counting how many electrons are there. So let's walk through some examples. So lithium's electron configuration is 1s2, 2s1. So we go across the 1s2 and then we hit down to lithium, and lithium is in the 2s and it's in the first spot. So if we find the highest energy level is 2. We count how many electrons are in there, and there's 1. So we'd say that there is 1 valence, lithium has 1 valence electron. Boron's our second example. Boron's electron configuration is 1s2, 2s2, 2p1. It's 2 spaces over from lithium, so we've filled both of the s's. We've moved into the p block. Boron is the first element in the p block, so there is 1 electron in the 2p level. Now, we have 2 separate orbitals, but both of them are in the second energy level. So all of those electrons count as valence electrons. So we have 2 in the s, and we have 1 in the p, which means that we have 3 total valence electrons. If we look at carbon, carbon's 1 more over, so we're just building on. So it's 1s2, 2s2, 2p2. It's in the second spot on the second level in the p block. So if we look at our highest energy level is still 2. We have 2 of the electrons in the s orbital and 2 of the electrons in the p orbital. Therefore, we have a total of 4 valence electrons. If we skip over a couple and we look at neon, neon's electron configuration is 1s2, 2s2, 2p6. Highest energy level is still the second energy level. We have 2 of the electrons in the s orbital. We have 6 of the electrons in the p orbital. So we have a total of 8 valence electrons. Now, 8 is our magic number when it comes to valence electrons. All elements want 8 valence electrons. So whether that's they steal them from another element or they share them with another element in the form of ionic and covalent bonds, they want 8 valence electrons. And we call that a full octet. So let's pick a different example, something that's not in the second energy level. Let's look at bromine. So I've used bromine's shortened electron configuration, mostly because of space. So argon's in brackets, so it has the same electron configuration as argon. And then we're going to keep adding on. So then to get over to bromine, it's 4s2, 3d10, 4p5. That's where bromine lives on the periodic table. So if we're looking at the end of this electron configuration, notice my valence electrons aren't right next to each other in the electron configuration. They're in the 4th energy level. So it's the 4s gives us 2 of our valence electrons, and our 4p gives us our other 5 valence electrons for a total of 7. The 3ds, even though they're written in between the 4s and the 4p, that's a lower energy level. 3 is lower than 4. We're looking for the highest energy level numbers. In this case, it's 4, and we have to remember that it's both the electrons in the s orbital and the electrons in the p orbital for a total of 7 valence electrons. So when we start looking at bonding, we draw something called Lewis dot diagrams or Lewis dot structures. And that's just a visual way to represent electrons and elements and how they're bonding. When we draw Lewis dot diagrams, we use dots to symbolize electrons. We're going to treat the electrons as particles, so we draw them as dots. And when you draw Lewis dot diagrams, you're only drawing the valence electrons. Everything else is pulled into the element. It's only the valence electrons that are involved in bonding. So those are the only electrons that we're going to draw in the Lewis dot diagrams. So let's go through our same examples. So our first element was lithium. We said that lithium had 1 valence electron. So if we were going to draw the Lewis dot diagram for lithium, we would draw 1 dot because it has 1 valence electron. So we write the symbol, and then we write 1 dot next to it. For right now, it doesn't matter where it goes, you just have 1 dot. If we move on to boron, boron has 3 valence electrons. Now we're going to draw these diagrams similar to how we filled orbitals in orbital diagrams. The electrons are going to go in singly first, and then they're going to pair up. So for boron, you're going to draw 3 electrons kind of in a box, kind of in a diamond shape, around boron. If we imagine that there is a box around our elements, eventually we're going to put 1 on each side, and then we'll go back and pair them up so that we have a pair on each side. So let's look at our other examples because that's going to help us visualize that. So carbon has 4 valence electrons. So following the same process of boron, you're going to put 1, 2, 3, 4. They go in singly around carbon. For neon, neon has 8 valence electrons. So we go 1, 2, 3, 4. Now I go back and pair them. 5, 6, 7, 8. Remember, neon has a full octet. All elements want to have 8 valence electrons. They want to have this full outer level. They want that 8. 8 is our magic number. And then our last example, bromine. Bromine had 7 electrons. So we're going to follow our same process. 1, 2, 3, 4, 5, 6, 7. So if we look at how many electrons they need to complete their octet, well, lithium needs a lot. Boron needs quite a few. Boron only has 3, so it needs 5 more. Carbon has 4 of its valence electrons. That's what makes carbon so special when it comes to bonding. Neon isn't going to bond. That's why noble gases don't react. They don't bond with anything else because they already have a full octet. They don't need electrons from anybody else. And then bromine is going to react fairly easily because it only needs 1 more electron to complete its octet. So that's how these valence electrons relate to how an element is going to bond.